So we'll see how it does. Ignore those error messages. All right, we're rolling. I have no idea. They don't exist. All right, so any other homeworks coming in, please turn those in before we start talking about them. Going, gone? All right, cool. So, so I graded question 10, and question 10 was a Turing machine that appends 1 to, I think it was the rightmost end of the number. So your basic idea is, and I didn't tell you where you started, but most people assumed that we were sitting somewhere over the number, which is a good assumption to make. If not, you've got to somehow get to the number itself. So the idea is wherever you happen to be, you want to move to the right and don't change your number, and keep doing that until you get to a blank. And then basically you just need to change that blank to a 1 and you're done. So here's one way to do this. Start in S0, and if you have a 0, go to S0, write a 0, and move to the right. If you're in S0 and you have a 1, stay in S0, write a 1, and move to the right. If you're in S0 and you have a blank, we can go to an undefined state like S1. We can replace that blank with a 1, and we could move right or left. It doesn't really matter. And that would suffice. But there were some other versions of this where things were done in pieces, and that was fine. As long as you ended up with the effect that this first blank basically gets turned into a 1, that's the correct behavior.
I thought it wanted me to change the last number to 1, so I stepped back.
Oh, okay. Yeah, so when you get to a blank, then you could go to S1. You could leave that a blank and move to the left. And then S1, whatever you have, write a 1, and doesn't matter how you go. Right? Or you could just leave this off, because if it's already a 1, you don't have to do anything. So that was question 10. And then question 11, was that replacing the first 2 consecutive 1s with zeros? Yeah, that's more challenging for sure.
If we would have drawn a state diagram, I didn't do that, but I really wanted to. State diagrams, flow charts.
Yeah.
That technically didn't go to correct answer.
No, I still wanted to see the list of states, right? So if you do both, that's fine. But I want to see the actual program for the Turing machine. But yeah, so what's the pseudocode? So move right till you hit a blank, or just assume you're starting at the rightmost bit. I'd let you get away with that too. Move left. If it's a 0, go into some new state, let's say S10. S10, if it's a 0, then we want to go to S20, which means replace with 1, 1. If it's a 1, you want to come back up here to where you're moving left looking for 2 zeros. So I don't have a really good way of designing these machines on paper. I don't have a flowchart mechanism that I'm fluent with, but that's my attempt at a flowchart. So S0, 0, go to S0, move to the right, write a 0 and move to the right. S0, 1, stay in S0, write a 1 and move to the right. S0 blank, go to S1, write a blank, and let's move to the left. So S1, looking for the first 0. So S1, if it's a 1, We're going to stay in S1, we're going to leave the 1 in place, and we're going to move to the left. So that's just looping over any 1s that we find. If you're in S1 and there's a 0, we're going to leave that, but we're going to go to S10, leave the 0 intact, and move to the left. And if we're in S1 and we hit a blank, then we can't do anything, so we could just let the machine halt at that case. So you don't need to list those cases. So S10, if we have a 1, we found a 0, but then it was preceded by a 1, so we're back to where we started from. So let's go back to S1, leave the 1 intact, and move to the left. If you're in S10 and there's a 0, now you found 2 zeros, and you're sitting over that second 0. So let's go to S20, replace that 0 with a 1, and move to the right. And then S20, if there's a 0, let's replace that with a 1 and move to the right, and go to S30, which doesn't exist, so it'll halt. And if there's already a 1 there, we could replace it with a 1, but it'll be an undefined state, so it'll halt in that spot also. So something like that will get you there. There's even more ways to make Turing machine state tables than there are to make C programs for ODPs and such. All right, there's a lot of wiggle room available. I really want to get rid of those little lines, but now I just broke it. Yeah, I shouldn't have done that. Yeah, we'll live with the little lines. So, any questions about any of the other homework problems?
I think it was the first one. It was like to make a venue for a thing. I just wanted to know how you would justify that.
So, can you tell me what the question said?
Oh, the one. How about the one? Make a language that describes 11 to the n, or 1 1 to the n.
1 1 to the n.
And after n greater than 0.
So parentheses 1 1
Yeah.
to the n bigger than or equal to 0.
I'm assuming this means any consecutive ones.
Yeah, so it's either the empty string, 2 1s, 4 1s, 6 1s, 8 1s, etc. All right. So so we need 0 and 1, which will be our terminals. We need a start symbol, and I don't know if we need a temporary state. Terminals will be 0 1. Start equals start. And then, so what did you think of for here? So S has got to go to something. Okay. S can go to 1A.
Yeah, that's pretty good.
Okay.
And then A would be 1B,
Okay.
and B is 1.
Okay. So that'll be a 1A, which will be a 1 followed by a B. So this will be a 1 1 followed by a B, which looks like 3 1s.
And then it should keep going.
So how do we make it keep going?
So
S to S doesn't get us anywhere because it says we can replace an S with an S.
maybe S and AS.
So that will keep us going. But I think it'll allow odd numbers of 1s also. So you had So S can be a 11A, which would be a 11, or it can be a 11 followed by a 11A, which could be.
To fix the zero, you could just have, instead of 1 1 on the S, you could have D and D go to lambda, or.
Well, you could just say S goes to 1, and that would do it within 1, if you want to do include one thing. So
Thank you.
that's where you take out the
In the
middle
case
line.
we want empty. That's what I was saying.
So,
Include the empty string.
You could have S also go to lambda.
or you could have S go to lambda. That'll get you the empty string. That should work. Any other ways to do this? So here's another option. S could go to lambda, or S could go to 1 1 followed by S. I think that would get you there. Well, I'm like rasterizing. That's awesome. Haven't seen that in like decades.
So it's fine.
Yeah. Got that shaky hand. Yeah, it's still just a regular symbol. It just happens to also serve as a start symbol, but we can use that like any other. So you'll definitely see a Turing machine question on the final, all right? Because that's a good thing to do, and you've all done the homework on it now. So, yeah.
I was wondering about question 1B, which, if I remember right, was 0 followed by, like 2 to the n.
So 0, 1, and it's just 1 to the 2 to the n? Okay. So kind of like this? Yeah, 2n? Yeah. So 0 followed by an even number of 1s. Is n bigger than or equal to 0?
I misinterpreted that. I thought you had to have a number of ones equivalent to 2 to the n, which was tricky.
Yes. Isn't that?
Even number,
Yeah, so that's kind of the same thing, though, right?
You're saying 0, 1, 1, 1.
well,
Yeah, I'm saying 0 followed by even number of 1s.
yeah, what I'm saying is, say if n is 3,
Oh, you thought it was a particular n.
no, what I'm saying is, in this case, if n were 3, then it would be 1 to the 6th, so 6, 1.
Mm-hmm.
If it were 1 to the 2 to the n, then if n were 3, it would have to be 8 ones.
Oh, okay.
So you basically double the number of ones with each increase in n.
Right, so if it's 2 to the n, that would be really interesting.
Yeah, that's what I
But
was trying to do, because that's how I read it on the paper.
But can we do that? Can we do a string of 1s where the number of 1s is a power of 2?
I tried to do that. I think my solution is a little bit shaky, though. So basically, I had symbols A through E.
Okay.
And my set of rules started with S goes to 0A.
Mm-hmm.
Then A goes to 1, 1. A goes to BC. D goes to DE. C goes to DE. D goes to 1, 1. E goes to 1, 1. DE goes to lambda. And BC goes to 4 ones.
Interesting. Does that work?
Something like, could you make that an infinite string, because it looks like there's no way to go back to, well, the B after you originally say A to B.
If you go far enough, the only symbols you'll be left with are D and E.
Yeah.
And you have to have D and E together to turn that into a blank space, and that's how I got around you saying, well, I could just change, some of these D's and E's to 1, 1 and leave others alone.
Yeah, but there's no recursion here. You're never going to get an infinite string.
So A is either 4 1s or it's a DE, DE, right?
So yeah, you'd be like.
Which, yes, so I don't think it'll go up to an arbitrary number, but I think you've got the idea here.
Or maybe if DE went to DE, DE, that would do it.
If there was a way to generalize this, right, like an array, where we could have more and more variables. The other thing is, I don't know if this is really well defined.
Yeah.
If we can actually say BC gets replaced with that. I think it depends on the type of grammar we're talking about. But we're usually just doing a single variable.
Yeah, that's one of the things I was concerned about, because I didn't see any example of that.
Yeah,
So
yeah.
I'm not sure if I could do that.
But that seems like it will get you there up to a certain value of n.
It did have a similar thing when we were doing another question at like A, B, and C. It said A, B can be replaced with B, C or something like that.
Yeah.
Or like A. Let me think about that.
But to do this, it seems like we want to take a string that's this long and replace it with 2 copies of itself,
Yeah.
right? But I don't know how we can force it to not end up somehow getting 3 copies of itself or 5 copies of itself.
You said B would yeah, have only one of them switch.
Yeah.
That's essentially why I did the 2 variables.
Right.
Opposed to lambda and not allow individual.
Right, so it doesn't split them up. That's cool. So if this is legit, right, then this is probably doable like that. That's pretty cool.
Yeah, I can imagine it being done with an infinite state machine.
Yeah, yeah. But this problem, right, which was what the problem was intended to ask, is pretty straightforward, right? It's just a 0 with the same thing that we had in the previous one. So bring your start symbol to 0A and then just write out your rules for A being an even number of ones. That would do it. Yeah.
Can you go over number 3, the DNS?
Was this BNF for
Scientific
scientific
notation.
notation? Sure. So what does scientific notation look like? It's, something exponent something, right? And what is this first something? What are some of the things that are valid before the E? So it could be, 4 exponent something. It could be 4.2 exponent something. It could be negative 4.2 exponent something. Do we want to allow something like 4 period exponent? I don't know. Do we want to allow this, or do we always want, digit period digit exponent something, where there could be multiple digits here? So you kind of have to decide up front what exactly are you going to parse for. And I didn't specify that because I wanted you to explore that space, right? So let's make this a Wild West kind of version of scientific notation, anything that looks reasonable for scientific notation. So let's just imagine some integer, possibly signed, so it could be a plus or a minus, followed by an integer, followed by an optional period, followed by another integer which is unsigned, exponent, and then an optional plus or minus, followed by an integer. I think that's the most general version of a scientific notation. So scientific notation could be so mantissa 1 followed by a period, followed by mantissa 2, followed by an E, followed by an exponent, or mantissa 1 followed by a period, followed by an E, followed by an exponent, or just so I'm calling this mantissa 1. Just mantissa 1 followed by an E, followed by an exponent. And if we wanted to allow a number without the E in there, like just the number 2, we could put extra rules in here. But I think that captures these cases. So mantissa 1 is it's a sign followed by an unsigned int, or it's just an unsigned int. And a sign could be a plus or a minus or, well, we don't need that. So a sign can be a plus or a minus. And then an unsigned int we can make is just a digit followed by 0 or more digits. Right, so we saw that when we were doing expressions. And M2 is just an unsigned int. And then our exponent is a sign followed by an unsigned int, or, sorry, a sign followed by an unsigned int, or just an unsigned int. And then an unsigned int is a digit followed by digits, or it's just a digit. And digits is a digit followed by digits. Something like that might work. Well, what kind of issues did you run into? Anybody?
Well, I couldn't figure out how to do one or more of a character, and so that was what I was doing.
Okay, you mean like this?
Exactly.
Okay, yeah.
I couldn't figure out how to do that, so I
Okay.
Do we necessarily have to specify all digits, like 0 to 9?
Technically, I mean, it depends on what's understood, but yeah, it doesn't hurt to say digit equals 0, 1, 2, 3, 4, 5. When you're actually writing code to do this, usually you have a set of primitives that are understood by the parser. So digits and symbols and alpha and things like that.
Just like in the theoretical space of this, are those rules like set a set? I remember the book used squiggly lines notation. I'm like, this is
Squiggly line notation.
and curly brackets.
Oh, okay.
They use curly brackets, which
Yeah, so
it's
you
like
could.
the digit equals 1 or 2 kind of thing.
Yeah, so there, I'm assuming some precedence rules here. So this alternation, the ors take highest precedence, right? So it's implicitly this thing or that thing or that thing. But you could group them together to make it less ambiguous. Monday, when I have my other laptop back, I can show you some code built on top of BNF in C. Just a little package I put together eons ago that lets you basically take a BNF and write code from the BNF to do parsing. And it's pretty cool to be able to work with because you can bundle these things up into executable modules for parsing input. Yeah?
How would you do that? How would you write something like this in C?
So the version I wrote, it was built on top of an old assembly language package called Trans from Digital Equipment Corporation back in the early 80s. And I fell in love with the Trans package. It was a way to parse things, and I wanted it for my own, so I translated it into C using a bunch of macro preprocessors. And that's what I can show you on Monday. Or in my office if you want. But there are tons of utilities out there that will let you take something like this, write a description of a language, and turn it into code. So the two main ones in Linux are Lex and Yak. So Lex is a lexical analyzer. Yak is yet another compiler. So it takes a description of a compiler and turns it into an actual compiler. So you can spit out compilers pretty easily with those two. I used to have a program someone wrote, it's called the Swedish Chefifier. You could put in text and it would translate it into something that sounded like the Swedish chef from the Muppets. And it was just a set of rules, but it was parsing and translating accordingly. All right, so PA2, I've been looking at those, and those look really good. I posted comments if there was anything that I wanted to ask you about your code, but they look great. So people were able to write even numbers as sums of two primes, with a lot of variation in how people did it, which was kind of interesting to see. Some people pre-generated the primes and stored them. Some people used a general prime number testing. Some people used a sieve to load primes into an array. Some people tested primality on the fly, different things like that. There are a few people who did not upload their output, though. Okay, so if you uploaded your code but not your output, what I'd like you to do is run your code, right, on whatever system it's running on, and then copy the text, right, and paste that into a document, save it as a PDF, upload that. Okay, and if you get to that today, I'll still grade it since I already got your code. And if that's not happening, come by and talk to me or send me a note and let me know what the issue is. But I want to see the output as well as the source code. Okay. And if there was a problem with your code, feel free to come by either at 11 o'clock class or office hours or whatever, and we can go through your code and figure out where it's hiccuping.
I just want to make sure you wanted the code as a PDF document, right?
I wanted everything in one PDF.
Okay, so you didn't want like a firefighter.
No. Just wanted to be able to look at it, and I can eyeball the code, and I can look at the output and that kind of thing. And we were talking before class about why I did that, and it was really just because I wanted you to have some leeway in how you implemented this. Some people did C++, right? Some people wrote several different files, and I didn't want to have to figure out how to compile, and I didn't want to insist on a make file and all this stuff. So I figured I'd let you write it, let you execute it, and then just show me all the stuff in a document. All right, well, let's talk about limits of computation. AKA the halting problem. So the halting problem is a really, really old question. It goes back to 20s. It actually goes back before that to the turn of the century, and David Hilbert and such. And it has a really fancy-sounding German name with about 80 syllables to it that I can't pronounce. But it translates to, I don't remember what it translates to, kind of to the halting problem. And it's a question of whether or not you can basically analyze an algorithm to extract certain information about it. And so in the language of Turing machines, here's how we can phrase the halting problem. We know that your system responds to the input on a tape, and it responds to a table of what the state transitions are. And as it moves the tape, it looks for a new state that matches the current state in the input, makes some change on the tape, changes state, moves the tape, keeps doing that. If at any point it gets into a state that's not recognized, either you're moving to a state that's not defined, or in your current state you can't find the symbol that's on the tape, the system halts. Okay, and that's the end of the execution. And so the halting problem is, given a program, so given tape, so the contents of the tape, and given the set of states, can we write some program, let's call it HP, that ingests those two pieces of information, the contents of the tape and the collection of states, and returns either a 0 or a 1, telling us whether or not this program will halt when it's fed this tape. So 0 equals, let's say, no halt, and 1 equals halt. So it's an analysis question. So let's modernize this to C, because C is in some ways equivalent to a Turing machine. And let's think of the question like this. Can you write a program that you can feed in the source code for another C program, along with, say, a file that contains the input you're going to give to that program, and tells you whether or not this program ever finishes? Does it run forever, or does it at some point execute a return from main or an exit, and the program ends? So an infinite loop detector, basically. And there's some cases where we can definitely do this, right? A short program, 10 lines of C code, we can probably look at ourselves and say this program will never exit, right? If it's got a while 1 equals 1 loop and there's no break inside, it's not going to exit. If it says for I equals 1 to 10 and we're not doing anything funny with I like changing its value, that is going to exit, right? If there's a final return at the end of the loop. But if it gets more complicated, right, while I is not equal to 0 and then there's some big long function we use to calculate the next value of I, it can be harder to know whether or not this program is going to finish. So the question is, can we make an analyzer that tells whether a program loops forever? That's the halting problem. And conventional wisdom for 50-ish years plus has been that you cannot do this. You cannot write a program that answers this question. And let me show you an outline of the proof, updated to something like C. So suppose HP is a function, and HP of some input and some program returns 0 if the program's not going to exit, and 1 if it does exit. So you come to me and you say, hey, I solved the halting problem. Here's my function, HP, halting problem. And if you call this function with any set of input and the source code for a program written in C, it will run, and eventually, right, in a finite amount of time, it will return either a 0 or a 1. If it returns a 0, it means this program does not exit. It loops forever. If it returns a 1, it means the program exits eventually. You've got to be able to do this in a finite amount of time. If your program never gives an answer, it's not really a solution to the halting problem. Okay, it might take 1,000,000 years, that's okay. As long as eventually it will give me either a 0 or a 1 back, it's a solution to the halting problem. Okay, so here's the problem with this. You've got this program, which means if we look at the source code for this program, which we're going to assume is written in C, there's some code in here that eventually is going to return 0, and you've commented your program, of course. So there's a comment here which says program never exits. And somewhere else in here, there's a statement which says return 1, which means that you've analyzed the program and the program does exit. And there's some other code in here also. But if your function HP is going to eventually return a 0 or a 1, there's a place or multiple places in here where eventually it returns either 0 or it returns 1, right? Okay, I'm going to modify your program. I'm going to make a new version of it. And I'm going to call this program HP2. And here's what I'm going to do. Down here where it says return 1, instead of returning 1, I'm going to say loop forever. And here where it says return 0, I'm just going to leave that as is. And now I'm going to take this program and I'm going to feed it to your halting program. And you're going to ask your program to analyze this running on itself. And one of two things is going to happen. Your code is going to eventually decide, hey, this program is going to exit at some point, which means it's going to get to this point in your code, at which point this program is going to go into an infinite loop and it's never going to exit. And your program gave the wrong answer because your program analyzed this and said it is going to exit, but in fact the program's going to go into an infinite loop. Or your program's going to say, I've analyzed HP2 and it is going to exit. Sorry, it's never going to exit, but at that point it's going to do, let me change this. It's going to do an exit statement. And again, your program has done the wrong thing. It's made the wrong prediction. So if you give me a program that you claim solves the halting problem, I can use that to construct a program that will trip up your supposed solution. And I'm doing it in the most simple way possible, which is by just deliberately forcing it to give the wrong answer.
This seems like Russell's paradox.
Yeah, it does. The solution in this case is that there is no such, the supposed solution in this case is that there is no such program that answers the halting problem successfully in all cases. I personally disagree with this conclusion, though.
You don't think this is a good enough solution?
I don't agree with this solution. I don't agree with it because the assumption is that if this program, HP, solved the halting problem, I can make these seemingly harmless changes to it, right? It's already made its decision by the time it gets here or here. So changing what comes after that shouldn't affect the behavior of this program. That's not true. I can write you a C program that prints something, and by changing the statement that comes after it, cause it to print something different. And I think there's an error in this assumption that this is a harmless, benign change that's not going to affect the behavior of HP. I claim it does. And it does specifically in the case when you're running this on itself.
Well, couldn't you have a program that instead of doing these changes, it just took the input and said if one, then loop forever?
Mm-hmm.
And wouldn't that do the same thing here?
But then presumably if you ran the halting program on that program, it could still analyze it correctly. The reason this is contradicting itself is because this is the actual program that's supposed to answer HP correctly. Right? Because without these changes, this is the program you came to me with and said this solves the halting problem. So if I run any program through this, it should answer the question correctly, which means if I run this program through itself, it should answer the question correctly.
But if it ran this, if you had, even if it did do it correctly and you ran this through it, what would happen? That's the paradox.
If it answered it correctly and you ran this through it,
Yeah.
it can't be answering it correctly.
Yeah, and such that the definition, I think, is that because there can't be a machine that answers everything correctly, thus a machine that can't answer everything correctly cannot exist.
Yeah.
I'm not seeing where the issue is.
Okay,
You're trying to modify code into
so let's try this a different way. Let's get rid of the function. Let's just make a program. So you're going to give this a program in C, and you're going to give it the input file that the program is running on, right? And it's going to analyze your code, and it's going to print out the program halts or the program doesn't halt, right? So somewhere it's going to print out the message it halts, or somewhere it's going to print out the message it runs forever. All right. So any program that you analyze with this code should correctly either tell you the program's going to halt or it's going to run forever. Okay, that's the assumption. So we're going to come into this program and we're going to make a new program, right? We're going to modify this, and after it says it halts, we're going to go into an infinite loop. And after it says it runs forever, we're going to do a halt statement, a segfault or something, to stop the program, or an exit. Okay, so the assumption is if this original program solved the halting problem, this new program should also solve it, right? Because we haven't changed any of the logic anywhere. All we've done is asked it to do something else after it's already made its decision. We either go into a loop or we execute a halt statement. But now, if we use this program to analyze this program, what is it going to conclude?
Oh, yeah.
Right? It's going to conclude that the program will eventually halt. But if it does that, it's going to print out it halts, and then it's going to go into an infinite loop. It got the answer wrong. Or it's going to conclude this program will run forever, and as soon as it says that, it's going to halt, and it incorrectly predicted the behavior of the program.
So is this the program that you're running to determine whether or not a program under it halts or not?
Mm-hmm. And you're feeding it itself as its own input.
Oh, well, in this case, if this is the program that you're running, not the one that you're analyzing, then it's no longer your halting problem program because you just modified it such that it no longer meets the definition of the halting problem program.
I bet you if you ran this into your original unmodified thing,
Yes.
the paradox would be...
Then there's no paradox, right? Because this will either loop forever or halt, right? The paradox comes from this idea that if we add these extra statements here, this is still as good as the original program that you had. And that's where I find an issue with it.
I would disagree with that because you specifically modified the program so that it no longer does what you wanted it to
Yeah.
do. So then it no longer fits the definition of that program.
Right, but why would adding a statement after it's already decided it's going to halt, why would that break the behavior of the program?
Here's the thing, if it's already decided, then it's decided in finite time, right?
Mm-hmm.
Oh, and then
Then that's just extra tacked
Yeah.
onto the end.
Yeah.
So technically, it's still finished in finite time and gave you your answer.
But this program didn't finish because it's going to, after it prints that message, go into an infinite loop.
Only in the technical sense.
Yeah,
Only in the technical sense.
Yeah.
It gave you your answer in finite time, which is what we're concerned with, right?
but it gave the wrong answer. It only took a finite time, but in a finite amount of time, it gave me the wrong answer. Right? It's not saying, will this print an answer in a finite amount of time? It's saying, will this program loop forever or exit? And this program loops forever if it gets down here.
So I don't understand why you have a problem with this.
Did you have something?
I see it both ways. I understand that like after you decide, so if you have like an integer and you set it to 2, and then you get to that print statement that says like print that this is 2, and you change it afterwards,
Mm-hmm.
it doesn't change that it was 2 at that point. So I see where Drake's coming from.
Right.
But since it has to do with the nature of the program, and the answer is reflective of how the program behaves, adding it afterwards sends it into that infinite loop, so the answer is there, right?
Right.
So it doesn't matter what it was at that point because it encompasses the entire program.
Mm-hmm.
I can also see what you're saying too. If you change this and make something that's not the original program, you can still pass this into the original program, and it will also cause the same paradox.
If you pass this in the original, it should work fine.
Well, no, because it's gotten to the same place the same way, didn't it?
But the original program presumably will give the right answer. I don't think you can force a paradox.
No, I think what it is if you go back to the original one where you return 1 or 0, and then make a program where if 1 loop and if 0 return,
Mm-hmm.
that will paradox your original program
Mm-hmm.
without modifying it.
But what stops the original program from successfully telling you whether this modified program gets here or here? I mean, it might still be able to do that.
Well, if you're using the same program and just kind of using that's output,
Mm-hmm.
then how it got to 1 or 0, I guess it would have to have an input.
So we're out of time here, but this is cool discussion. If you want to see my argument on this, go ahead and Google my name with halting problem after it, and I've got a paper published on this. Well, unpublished but posted, that I've never been able to get anybody to look at seriously. All right, so I'll see you next time, but we can keep talking because I'm going to be here for another hour.
So, just to make sure I've got it right, this is the code that we're running, not what we're analyzing.
It's both,
Okay.
right? This is being fed itself as a program to analyze, so we're asking it to analyze itself.
So in that case, isn't this just a bad problem? Because if the original unmodified one that doesn't go into a while one version doesn't.
The contradiction proves that this will not solve the halting problem. The unspoken detail is that if this does not solve the halting problem, then that original one does not solve the halting problem. That's what I have an issue with. Yeah.
It's like if I turned in a programming assignment and then you stuck a while one in and then graded me down for that.
Right. Yeah. And I have some sample code in that paper I mentioned that does exactly this. Program works one way, and then you add something after it already prints, and it actually changes what it prints in the prior statement.
I can see what you're saying, and like this is a different program.
Yeah.
But I think the paradox, the way it was originally proven, is you were able to run this, or you doing something similar to this, but run this into the unmodified program.
Mm-hmm.
It would freak out.
Right.
Or it would return the wrong answer.
Right.
So using this code as an input to the original solution would break it.
Mm-hmm.
Thus, there cannot be no original solution.
Right.
But how would it break the original one?
Because it got to
Isn't the original one supposed to take any piece of
Yeah, it may not break it.
it takes any piece of code.
And the original one is still a valid halting problem
Yeah.
solver.
But it got to this printf and the other printf in the same way. And
Well, yeah,
they
that's
both
the
belong to the same.
that's the issue here. Is does adding this somehow change the logic, and could it cause it to get, instead of getting here, get down here? And I think that's exactly what it does. Because if you really, go ahead.
I'm sorry, I interrupted.
No, go ahead.
I was going to say, unless your original halting problem solver looks specifically for its own code and
Yes,
goes through there,
which it's going to have to do.
or will it have to look for, say, printf if halts? If it knows how a printf statement works, for example,
Mm-hmm.
can it just look at, essentially, I would assume that your halting problem would have to be able to look at arbitrary code and break it up into components and leave
Yeah,
out some of the details.
something like that.
Otherwise, you'd have to have an infinitely long halting problem.
Mm-hmm.
So I would think that the specifics of what the code does in terms of determining whether or not something halts shouldn't really matter. You should be able to pick up on that there's a while one loop in the code, and if you eventually get to that point.
Right. But I feel like if it's going to work on all programs, including itself, it's going to need some information about itself. Because I think that's an edge case. And if you change your code, you can possibly trip it up into not recognizing itself and doing the wrong thing. And that's what that paper basically plays off of. It gives some examples. But I sent it into a journal and got a review back, and it said the author clearly has no understanding of mathematical proof, and that was the only comment. So.
No, I think, okay, yeah, my original solution, I think I'm remembering, is that it was just a predictor whether we were returning 1 or 0. And
Mhm.
just plugging a NOT gate into the end, and then compiling that as a bigger code and turning that in would break it.
Mm-hmm.
But I think if you did something here, where if you had, because I'm thinking if you actually wanted to do this like this, you'd have to have an input for the input.
Right. That's another issue is this sort of recursive.
I don't think that's how the original proof would have worked. I think it has something to do with a NOT gate or something like
Mhm.
that. Just if true, then return false.
Yeah.
Or if loop, then break, something like that.
I mean, this is basically a diagonalization argument, right? It's how we showed there's more reals than there are integers. It's how you get to Russell's paradox. It's going down inside and then twisting something at the very last minute to force things to go wrong.
But see, I'm still kind of hung up on, the halting program code itself being an edge case.
Mm-hmm.
You can write a C compiler in C, right?
Mm-hmm.
And compile that compiler
Mm-hmm.
in C again on the C
Right,
compiler that
right.
you just wrote. And it shouldn't mess anything up, right?
This is true.
So I would think that if you have something that analyzes a program, itself shouldn't be an edge case.
The only possible rabbit hole here is that we need to feed this the program, so that's just a big string of C code. That's easy. But we also need to feed it the input that it's going to run on,
That's
which is, yeah.
there could be potentially, well, if there's an infinite number of inputs, then presumably the program goes on infinitely. But
Yeah,
there could be a lot of input and a lot of different combinations, which would make it take a very
yeah. And this is part of that soup that was percolating when cell matrix came into existence in the 80s, was this idea of having this infinite descent of this thing analyzing this thing, trying to break that and get something that actually can like introspect and analyze itself. That was where cell matrix came into being.